Reusable rockets start with a simple, uncomfortable truth. For most of the space age, we treated the most expensive part of the vehicle like a paper cup. The first stage did about 90 seconds of brutal, high-thrust work, then turned into high-tech trash falling into the ocean. Each launch scattered tens of millions of dollars in engines, tanks, valves, and sensors across the seabed, all to deliver a relatively small upper stage and payload into orbit. To understand why reusing that hardware is such a big deal, you have to start with the math that has quietly run the show since the beginning: the rocket equation. Getting a spacecraft to orbit requires a total change in velocity of roughly 7.8 kilometers per second, plus margins for drag and gravity losses. The only way to get there is to throw propellant out the back at very high speed, and the equation punishes you exponentially for every extra kilogram you ask the rocket to carry. Reusability means deliberately adding structure, fuel, landing gear, and guidance hardware that do nothing for the payload and exist solely to bring the booster home in one piece. Traditional expendable rockets exploit that equation ruthlessly. They burn almost every drop of fuel in the first stage to push the upper stage as fast and high as possible, then let the empty shell follow a long ballistic arc to a convenient patch of ocean. A reusable booster has to behave more like a disciplined runner who slows down early for the return trip. It must reserve a chunk of propellant, often on the order of 10 to 15%, of what an expendable design would happily spend on ascent, to reverse course, survive re-entry heating, and cancel out the last hundreds of meters per second, right above the landing pad. That trade has deep consequences for design. Instead of a few huge engines that run flat out and never need to restart, modern reusable boosters rely on clusters of smaller engines with wide throttle ranges and reliable ignition cycles. On the pad, most of them light together to produce thousands of kilonewtons of thrust. Later, when the mostly empty stage is diving back toward Earth, only one or a few engines need to relight at a fraction of their rated power to provide a gentle braking force. If the engines cannot throttle low enough, the rocket cannot land. It will either hover wastefully or accelerate upward again. The flight itself splits into chapters. At liftoff, the booster has one main job: deliver the upper stage and payload to the correct separation point while staying within structural and thermal limits. It punches through thick lower atmosphere, where dynamic pressure hammers the vehicle and slight steering inputs cause big aerodynamic loads. As the air thins and the vehicle accelerates past a kilometer per second, guidance shifts toward shaping the long downrange arc, aiming for a stage separation around 70 to 80 kilometers up, with the booster traveling several kilometers per second. Once the upper stage separates and lights its own engine, the booster's second life begins. It still has lots of horizontal velocity, carrying it away from the launch site, and it is still climbing for a while before gravity wins. To come back, it must rotate so that the engines face its direction of travel and perform a boost back burn. Using a subset or all of its engines, the booster fires against its own motion, bending the ballistic arc into a loop that will intersect either a landing pad on shore or a drone ship at sea. The longer you wait to perform this burn, the more velocity you have to cancel and the more propellant you burn. Guidance gets trickier as the booster falls back toward the upper atmosphere. To stay controllable, it has to maintain a useful orientation rather than tumbling like a dropped pipe. Small cold gas thrusters near the top of the stage provide rotation control outside the atmosphere, firing jets of inert nitrogen to roll-less, pitch, and yaw the vehicle. As the air thickens again, large grid fins swing into position. These lattice-like control surfaces act as aerodynamic brakes and steering paddles, generating just enough lift and drag in different directions to nudge the falling cylinder back onto the correct path. Re-entry itself is another major hurdle. Even though the booster is coming back from a lower speed than the upper stage, it still hits the air fast enough to build a bow of compressed, superheated gas under the engine section. A short re-entry burn using a few engines does double duty. It reduces velocity to curb heating and uses its exhaust plume to push some of the hot gas away from vulnerable structures. Engineers thicken and reinforce key areas around engine bells, plumbing, and attachment points to survive that thermal and mechanical abuse over and over. Below about 10 kilometers, the atmosphere does most of the slowing, and the booster begins to look almost graceful. The grid fins work hardest here, trimming out crosswinds and small errors in trajectory. Inside, the flight computer is constantly fusing data from an inertial measurement unit, GPS receivers, radar altitude sensors, and barometric readings to answer 3 questions many times per second. Where am I? Where should I be? And what engine and fin commands will move me closer without overshooting? The most visibly dramatic moment is the landing burn. But from the computer's point of view, it is just another control problem with very tight margins. At a pre-planned altitude and speed, the center engine ignites, sometimes with 2 neighbors briefly lit, and then shut down to fine-tune thrust. Throttle ramps down as velocity drops, chasing a target profile that will bring the booster from a few hundred meters per second to almost 0 in tens of seconds. Near the end, landing legs made from aluminum and carbon composites swing out and lock, turning the bare cylinder into a tripod or 4-legged stance strong enough to absorb the final impact. If everything has gone well, the engine shuts down almost exactly at the moment the legs touch the deck. From the outside, it looks like a magic trick. From the inside, it is the payoff for thousands of small decisions about margins, sensors, and software. Each successful landing feeds a mountain of data back into the system. Temperatures logged at critical points, engine performance over multiple restarts, tiny deviations in guidance that might hint at hardware aging or calibration drift. Over time, a particular booster stops being new hardware and becomes a known personality, with a history of small quirks that the team understands. All of this would be nothing more than an impressive party trick if the real work stopped at landing. The difference between we can land a booster and we can reuse a booster economically lies in the hangar. After every flight, technicians roll the stage into a controlled environment, drain remaining propellant, purge lines, and begin inspections. They borescope engine chambers and turbopumps, ultrasound structural members, inspect welds, and review sensor logs. Certain parts are life-limited and replaced on a schedule regardless of how healthy they look, because the cost of failure in flight is far higher than the cost of a conservative swap on the ground. The goal is not perfection. It is predictable, repeatable work. Early reusable programs like the Space Shuttle proved that you can bring back large elements of a launch system, but still spend enormous amounts of money and time refurbishing them between flights. Panels had to be removed by hand, tiles inspected one by one, engines torn down and rebuilt. Modern boosters are designed from the beginning with access, modularity, and inspection in mind. Fewer fasteners, standardized interfaces, and robust protective coatings are all quiet enablers of faster turnaround. Economics sneak into every engineering decision. Extra structure for strength adds mass and cuts payload. Extra sensors improve fault detection, but cost money and maintenance time. Simpler mechanisms are easier to refurbish, but may impose operational limits. Program managers and chief engineers spend a lot of time deciding where to spend their limited margin. On a thicker engine wall here, on more generous abort criteria there, or on a more powerful ground test regime that can catch problems before flight. The right answer depends on what you are launching, how often you are flying, and how much risk you are willing to tolerate. Different rockets explore different corners of that trade space. Some, like legged boosters that land on drone ships, accept the massive landing gear and extra fuel in exchange for flexibility and where they can come down. Others pursue bolder ideas, such as catching the returning stage with mechanical arms attached to the launch tower. Eliminating landing legs saves mass and simplifies the engine section, but the timing, structural load paths, and safety margins for the catch system become absolutely brutal problems. Those designs shift complexity from the vehicle to the infrastructure, not remove it. Next-generation vehicles push these ideas and expose new difficulties. Fully reusable architectures with both booster and upper stage design to come back multiply every challenge of guidance, heating, and refurbishment. Stainless steel structures promise toughness and low cost per kilogram, but demand careful handling of cryogenic propellants. Methane engines offer cleaner reuse than kerosene, but bring their own combustion quirks. Larger boosters driving heavier payloads magnify everything. Plume impingement on the pad, loads on the launch tower, and the shock on landing legs or catch systems when hundreds of tons meet steel with seconds of margin. Not every mission is a good candidate for reuse. Small rockets carrying light payloads to very high orbits often cannot spare the delta V to reverse course and slow down. Squeezing in the extra propellant would push the vehicle beyond practical size or cost. Some deep space probes ride on expendable stages because the launch cadence is low and the risk tolerance is razor thin. In those cases, squeezing the maximum performance from a simpler, disposable first stage makes sense. And the booster's one-way dive into the ocean is a conscious choice rather than negligence. Over time, flight history starts to answer questions that no spreadsheet can settle. As boosters complete 10, 15, or more flights, engineers get empirical data about which components truly wear out and which were over-designed. Refurbishment procedures tighten up, steps that never catch problems are removed or automated, while inspections that pay off repeatedly get more attention. Insurance markets respond to the demonstrated reliability of reused hardware, and customers become less nervous about putting their payloads on a veteran booster rather than insisting on a factory-fresh stage. Reuse shifts from curiosity to routine. The real strategic prize of reusable boosters is launch cadence. When a single rocket is retired after one flight, ramping up access to space means building more rockets. When boosters come back and fly again, ramping up means improving factories, maintenance lines, and scheduling. That shift makes it realistic to imagine orbital fuel depots topped up by many small deliveries, modular space stations assembled from multiple flights, and surface outposts resupplied regularly instead of in rare, giant bursts. Logistics, not fireworks, become the limiting factor once hardware can be turned around reliably. Every reuse stage carries with it the culture that built and maintains it. Companies and agencies that succeed with reusability tend to be those that treat failure data as an asset instead of a source of shame, that write checklists, track small anomalies, and let young engineers point at awkward plots in meetings without fear. The glamour will always be at the pad, where engines roar and plumes billow. But the future is decided in long, patient conversations in design rooms and in the quiet tap of torquey wrenches and hangars. From the outside, reusable rockets can look like a flashy trick that belongs to a handful of modern companies. Up close, they are an evolution of traditional virtues. Meticulous craftsmanship, conservative margins where they matter most, respect for physics, and a refusal to waste hard-earned material and knowledge after a single use. The hardware comes home from the edge of space marked by heat and stress, and a team of people does what good mechanics have always done. They look closely, they fix what is worn, they replace what is doubtful, and they send it back out only when it is ready to work again.